We'll start with an application to motivate the idea of adding, subtracting, multiplying, or dividing functions. In this case, we have a function that represents the revenue and a function that represents the cost, both represented in dollars for sales of X units of a product. Then we're asked to calculate profit according to the idea that profit is defined to be revenue minus cost. We get that by subtracting the cost function from the revenue function. First, we're going to just evaluate P of 2100. Note that if P of X is defined to be R of X minus C of X, then it makes sense that P of 2100 is going to place the same value, 2100, for X in both functions. So it's going to be R of 2100 minus C of 2100. So we just use the same input for both functions and subtract the results. Very simple definition. Here we have 2100 as an input for the function revenue and 2100 as an input for the function cost, so that P of 2100 is equal to 59,850 minus 19,500, which comes out to be 40,350. And now, of course, to interpret the result, we want to just use the numbers 2100 and 40,350 with the word profit and with the appropriate units on each number. So translating this from left to right tells us that the profit from 2100 is our value of X, which is the number of units. So we'll say 2100 units. Next, we're at the equal sign, which generally translates into a form of the verb to be. Is usually safe. Is, was, were, are, am. And our profit is measured in dollars, so we'll go ahead and just put a dollar sign on this 40,350. So the example we just looked at was subtraction, but all four main operations work in essentially the same way. We say that we can create a new function f minus g, which in this case was profit, by taking the results of f of x and g of x and simply subtracting them, so that we apply the same x, right? This is the same x as this. The domain for both addition, subtraction, for all three: addition, subtraction, and multiplication, the domain is going to be all x that are in the domains of both f and g. And this makes sense because you can't really add f of x to g of x unless you have a value for f of x and you have a value for g of x. Division works very similarly. The only difference is that for the domain we also have to consider the denominator. We need to make sure that the denominator can't equal 0. So we get the same statement here, but we have to add the provision that g of x cannot equal 0. That's supposed to be an x. It helps to see what this looks like with functions that are defined symbolically. So if we take, for example, f of x equals the square root of x plus 1, and g of x equals the square root of x minus 5, then if we're asked to find f minus g of x, I'm going to take f of x, square root of x, plus 1, minus g of x and actually just subtract the formulas. Very simple definition, right? I do need to distribute this sign into the parentheses here with both terms. That's probably the number one source of errors because we need to put those parentheses there ourselves in order to remember to do this. So that gets us the square root of x plus 1 minus the square root of x plus 5. I'm going to simplify this before I put something in for f minus g of x, but before I cancel anything out, I have to find the domain. So I find the domain in this form, or the original form, but we need to find it before canceling anything out. So this has two square root of x terms, and each of those require that x be greater than or equal to 0. So my domain for this is from 0 to infinity. Even though when I simplify it, I see that those two square root of x terms actually drop out, and I end up with just 1 plus 5, which is equal to 6. So this is a constant function, but it has a restricted domain, which we wouldn't expect from a constant function. So let's do f times g of x. That means we're going to take the formula for f of x and take the formula for g of x and just multiply them together. We can use FOIL to do this. So that first term is the square root of x times itself, which is like saying the square root of x squared. The outer term will be minus 5 times the square root of x. The inner term would be plus 1 times the square root of x. And the last term would be minus 5. Again, I'm going to find the domain before simplifying. I can see that again I have square roots of x showing up, so for similar reasons my domain is going to be from 0 to infinity. This square root of x term at the front simplifies to just x. Technically, well, yes, technically just x. We've already taken care of the fact that it's got to be greater than or equal to 0 based on the domain. So this becomes just x. These two terms combine to give me minus 4 times the square root of x. And this last term, minus 5, stays as it is. So my result will be x minus 4 times the square root of x minus 5. For f over g of x, I'm going to again take f of x and put it over g of x. And in this case, there is no simplifying that can be done. Most of the work here is going to come from the domain. The fact that I have square root of x on the top and bottom tells me that x can't equal 0. However, I get an additional restriction coming from the denominator. The fact that I have x minus 5, or sorry, the square root of x minus 5 in the denominator tells me that the square root of x minus 5 cannot equal 0. I'm sorry, I said can't equal 0. I was thinking about the denominator already. The fact that I have square root of x really means that x must be greater than or equal to 0. But this not equal to 0 is correct in this part, that x, the square root of x minus 5 cannot equal 0. So let's go ahead and solve that as an equation. That tells me that the square root of x cannot equal 5, and then if I square both sides, that gets me that x cannot equal 25. So x is greater than or equal to 0 and is not equal to 25. If I want to just draw that on a number line, I'm going to see that I have 0 here, I have 25 over here. I can have a square bracket here, but I have to remove 25 from my set So everything in between 0 and 25, everything greater than 25 is all in my domain. So this is what it would look like in interval notation. If I wanted to put this in set builder notation, I would just have to put both of the statements together with an AND. So I'll write that as the set of all x such that x is greater than or equal to 0 and x is not equal to 25. Evaluating a sum or difference or product or quotient of functions from a graph is more similar to what we did with the numeric example with profit, revenue, and cost at the very beginning. We want to apply that same input value to both functions. So f plus g of 3 is the same thing as f of 3 plus g of 3. If I write it out this way first, then it's a very simple problem of just looking at the graphs and evaluating both functions for the input 3. So here's 3. It looks like the function f takes on the value 1 at x equals 3, and therefore f of 3 is equal to 1. This plus will carry down, and looking then at the function g, we can see that it takes on the value -2 at x equals 3. So 1 plus -2 gets me -1 overall. We can switch colors now and do f times g of 0. Try pausing this and doing it yourself first, and then check to see if you get the same answer I do. I'll write this as f of 0 times g of 0. Starting at x equals 0, trace up to the function f, and I can see that f of 0 is equal to 2. The times symbol comes down, and starting again at 0, I can see that g of 0 is equal to -3. So 2 times -3 gets me -6 as my final answer.